So I'm going to go through an example using the conservation of momentum formula that we see here, which tells us that the initial momentum of the system before a collision is going to be equal to the final momentum of the system after a collision has occurred. Now, one thing that I would recommend doing if you have a tendency to get values put in the wrong location in the formula is to make yourself a chart. And on the left-hand side, put initial. On the right-hand side, put final. And then put mass 1, velocity 1. And then mass 2, velocity 2 down the center of it. And then use this chart to record the numeric values in their appropriate places. So if we come back to the question here, it says a 3.7 kilogram ball has a velocity of 5.3. I'm going to let that be object number 1. So my mass is 3.7 and its initial velocity is 5.3 meters per second. Okay. It then tells me that it strikes a 2.8 kilogram ball that was at rest. So my mass of object 2 is 2.8 kilograms. And because it was at rest, that means my initial velocity would have been 0. Okay, then after the collision, the balls stick together. What is the velocity of the balls after the collision? Now, you might be wondering, how can we figure this out if I have 2 unknown values? So I know my masses of each mass isn't going to change, but I have a vacancy here for the final velocity for object 1 and the final velocity of object 2. Well, what you have to recognize is because they stick together, that means they are going to be moving at the same velocity. Okay, so these values are going to be identical. Now, there's a couple different ways you can look at this. I would still recommend just starting like normal and putting all of the values on the left-hand side. They go to the left-hand side of your equation. So I'm going to start with my mass of 3.7 times my velocity of 5.3 and add that to my mass of 2.8 that was at rest, so its velocity is 0. Now on the right-hand side, those would be my values on the right here. I'm going to have 3.7 times x, because I don't know how fast it's going, plus 2.8 times that same x. And I can do the same variables here because they stuck together and they're moving at the same speed. So on my left-hand side here, I'm going to go ahead and compute that out. So 3.7 times the 5.3, add it to 2.8 times 0, which is 0, gives me a 19.61. And now if you think back to your basic algebra, because these have the same variables, we can go ahead and add those coefficients together. So 3.7 plus 2.8 is a 6.5, and then we still have our x attached to there. Now to solve this, all I need to do is divide both sides by 6.5. So take my 19.61 divided by 6.5, and I get x to be equal to 3.01692. If I look for my significant figures, it looks like I get 2 significant figures. So I would have a velocity of 3.0 meters per second. Now, another common way that you will see people solve this type of problem is they might write the second half of this equation as mass 1 plus mass 2 times that final velocity. And that is actually still the same thing that we did right here. Okay? I just wrote it out using the original formula, but it is the same thing. If I were to take mass 1, 3.7, plus mass 2, 2.8, and then times it by that unknown velocity, well, 3.7 plus 2.8 still gives me a 6.5x, which matches exactly what I have right here. So even though the formulas look quite different, they are equivalent. So you have to just decide which formula makes most sense to you and which method of solving them when you decide what to use.